Today we're talking about polynomial functions. So far I haven't taught you too many things that you know how to graph, just a handful of basic functions with transformations, but two specific kind of functions that you do know how to graph are lines like 2x minus 1. We know that what that graph looks like just by looking at it. And then we also learned what happens if you tack on an x squared, like for quadratic functions. So like if I add on a 3x squared here at the front. With polynomials, we want to ask the question, what happens if I keep on increasing this exponent? So what if I happen to add on an x to the third, or negative x to the fourth, or 5x to the fifth? What is this graph going to look like? Is there any kind of generalizations that I can make? So these lines that we know about and the quadratics actually qualify as polynomials. So let's see if we can learn a few things that we know from these graphs so we can generalize to polynomials. When I look at f of x equals 2x minus 1, I know that that's a line and it's got a positive slope. It's going to look something like this. And then by contrast, g of x, I look at that and I say, that's got a negative 1/3 slope. So I know that it's going to look like this. Okay. All right. Then with the x squared graphs, I know that h of x is going to look like this because it's got a positive x squared term. And I know j of x is going to open downwards because it's got that negative 2x squared. All right. So notice that to draw all four of those graphs and figure out where the arrows are going, I didn't have to look at anything but the first term, right? I figured out by looking at 2x and negative 1/3 x, whether the line was going to rise left to right or fall left to right. Same thing with whether the parabola was opening upwards or downwards. I only looked at that first term and I ignored the rest of the terms. We know that those have to do with where the vertex lands. We know that that has to do with the y-intercept of the line. But as far as where those arrows go, what we call the end behavior, far left hand, far right hand, arrow behavior, that is all determined by that first term. And it had to do with what we call the degree and the leading coefficient. The degree and the leading coefficient. So the degree is the highest power of x present in the function, highest power of x. And we looked at that without even thinking about it. When it was x to the first, this was a line. We knew it was going to be a straight line going either way. And then with the x squareds, the highest power of x was the squared. And that's what told us the shape was going to be a parabola. And then we had to look at the leading coefficient, right? The leading coefficient is just the coefficient that's stuck to the highest power of x. Okay. So this is the coefficient of the highest power of x. Okay, for f of x and g of x, positive and negative tells you it's got a positive slope or it's got a negative slope. For h and j of x, positive leading coefficient stuck to the x squared meant it was opening upwards. A negative leading coefficient means it's opening downwards. Okay, so with just looking at the degree and the leading coefficient, we can tell what the end behavior of the graph is going to be. The main skill I want to get out of this video is for us to be able to identify degree and leading coefficient of any polynomial that we look at. All right, so the degree, remember, was the highest exponent in the whole polynomial. So for f of x, that is the exponent that's living in this term. That's the biggest exponent that I see. So the degree is going to be the exponent, which in this case is 3. So when I ask you for degree, don't say x cubed, you just say 3. It's a degree 3 polynomial. Then the leading coefficient is just going to be the number that's stuck to the x cubed term, and that's going to be 2. All right, so just go on a treasure hunt here. What is our leading term here? I kind of hit it in the middle of this one, right? That's the highest exponent is a 4, so this is a degree 4 polynomial. And our leading coefficient is the number stuck to that term, negative 6. All right, our last one looks a little bit tricky. H of x equals to 3. This is actually just a horizontal line, y equals 3, but it still counts as a polynomial. So what is its degree? Well, it doesn't have an x that I can see, but it does kind of have a phantom x to the 0. Remember that anything to the 0 equals 1. So we would call this a degree 0 polynomial. It's not a very interesting polynomial. And the lead coefficient would just be the number stuck to that x to the 0, which is the 3. The last thing that I want to talk about in this video is generally what polynomials look like. All right, so I'm going to hop over to Desmos and take a look at a bunch of them. All right, so I've got more polynomials graphed here than you might want to look at. And the first one is one that we're familiar with. It kind of looks like a squished version of x cubed because my y-axis, look, I'm counting by 20s on the tick marks. Polynomials tend to get humongous y-coordinates really, really quickly close to the origin. All right, and then let's graph another one. That one kind of looks like a transformation of x cubed. I got another x cubed graph. Okay, this one's been flipped upside down. It's got a couple of x-intercepts to look at there. Another x cubed. Let's increase the exponent here. So one thing you might start to notice here is that as I increase the degree of the polynomial, it has a little bit more opportunity to wiggle around in the middle. All right, so this one is an x to the 4th polynomial. There's another x to the 4th. Again, lots of wiggling going around in the middle. An x to the 5th. It kind of looks like it's got a little x cubed graph stuck there over to the right with some other stuff going on. X to the 6th. That one's wiggling around really flat around the middle. It's got some symmetry to it. A lot more wiggling on this one. This one didn't have a lot of wiggling to it. Kind of looked almost like a downward opening parabola, right? And then back to wiggling a lot, okay? But the main thing that I want you to notice about all of these graphs, I'm going to turn them all on and make just a big pile of spaghetti. All right. The one thing I want you to notice about these graphs is that, number one, they are what we call smooth, all right? So there's no corners to them like an absolute value graph, okay? They're kind of like a roller coaster. They're very wavy in the middle. They're also what we call continuous, which means all of these curves from left to right, I could come along with my pen and I could draw them all without picking up my pen. They're what we call smooth and continuous. All right, so I just want to write that down as a rule that polynomials are always smooth and continuous. Okay, smooth, meaning like a roller coaster. You never have a roller coaster shaped like a absolute value graph. And continuous, it means you can draw it without picking up your pencil. All right, so we'll figure out more in the next video how to determine what the graph of a polynomial looks like.